Hey, good afternoon, everyone. This is Celso Batalha, and I would like to go over a few things we brushed through the class, and I would like to offer some more options for you. So, if you Google NNAP modules, there are good astronomical resources there. So, the rotating sky is a basic one. It helps you to visualize the sky and the motions that we show last or on Tuesday using Starry Night software. So you have on view the celestial sphere. This is the celestial sphere, and if you take Earth North and South Pole and Earth axis and extend that onto the celestial sphere, you find and define the North Celestial Pole up and here. And also, if you take Earth equator and then you extend that out to infinity, you define the celestial equator. So those are basic things, and you should be able to reproduce these for the quiz. For instance, one of the possible quiz questions I could ask you is, can you please um, indicate the celestial points in a diagram? So you should be able to come up with the North Celestial Pole, South Celestial Pole, celestial equator, Earth in one point in there. Now, here's the thing. So, how can we uh, transpose this idea of celestial sphere to us that happen to be in a flat floor, apparently? So let's go to, for instance, San Jose, 37 degrees latitude north. So I don't remember the longitude. West is 122, I think, something like that. So let's see if I got it right. Earth's rotating there. Oh, not so bad. So that's this white dot represents us in San Jose, let's say. So if you're in San Jose, look at this other sphere right here. Okay. So if you face south, so your back is to north, right? And let me send a star somewhere here. Star, can I produce a star? Star control. So say put the Big Dipper and another star, some other star. Okay, so I'm putting stars in the sky. So here we are in San Jose. Our back is to north. We are facing due south, and stars rise in the east. See that? And then they reach maximum height when they cross a line we call meridian, and then they set in the west and they go below horizon. So this line over here that I'm showing you is the horizon. Okay, horizon. And so in there is a coordinate system that's called horizon coordinate system. So the horizon coordinate system is based on two positions. One is the azimuth, and the other one is the altitude. And you should be able to know those things. And I will go back to that in a little bit. So let me stop this motion right now. There. Okay. So in fact, let me keep the animation going. If you look on the left hand side, see the celestial sphere is not moving. So the stars, they stars do have motion, right? But they are so far away, we cannot distinguish this motion just by looking at them. What really happens is planet Earth, as you can see in this animation, rotates on its axis. And as a result of this rotation, we see stars migrating in the sky, we see the sun rising and set. We have days and nights as a result of Earth rotation on its axis. Okay. All right, let's stop the animation now. See if I could go. Now, see what I'm doing here? This person right here on the center of this horizon coordinate system, look at this star, and then what this person do, it draw a line from the highest point in the sky for that person. The highest point in the sky for that person has a name. The name is zenith. Zenith. So if you take the zenith, connect the zenith as we see to the star, and make a right angle with the horizon, and keep sending that towards the nadir, which is straight down, right? So we don't see the nadir. But if you go from the zenith through the star and to the horizon, making basically a nice right angle down here. So the angle between the person, the star, and the horizon is called altitude. Altitude, and is here given 37.1 degrees. Okay, 37.1 degrees. Now, if you find your north, your true north, and then you count the angle going through east, 90 degrees, through south, another 90 degrees, 180, and all the way to where that star projects itself down here, we have the azimuth, 247.9 degrees. Let's see if I can get another star. Oops, pause animation. Let's take this star over here. This star, the altitude angle will be bigger, right? Let's see. And it is. And the azimuth angle is kind of the same. How about this star over here? So the altitude, we can't see that star. This would be funny, right? But how about this star? Oh, we just did. Let's get more stars. As you can see, the altitude angle diminish, and azimuth is being reset. And it's going to reach maximum altitude, and then it goes down. Okay, so altitude angle, it's not necessarily 90 degrees. 90 degrees will be if a star happened to cross overhead. Let me take this star over here. Oh, there you go. So this star will have an altitude when it crosses up here that's going to be pretty much close to 90 degrees. Let me see if I can even put in a different perspective. It's going to be pretty much close to 90 degrees, the altitude. So altitude at that point, altitude and azimuth are, let me try again, I missed. Altitude and azimuth are coordinates based on the horizon coordinate system. Almost there, huh? See this angle down here? Almost 90 degrees. A little bit more. Okay, now it's going down. See, it's 90 degrees would be if the star is crossing exactly overhead. Okay. All this apparency is because Earth itself is rotating. Now, a more universal, if you will, system is what we are going to show us in a second, and that is the one that is based on equatorial coordinate system. So to go to the equatorial coordinate system, let me show you something before. Is another animation also in this web page. Here's Earth and the axis of rotation. So in the previous animation, the axis of rotation was kind of a sticking up, and here it's tilted because that's the case. If you take the system Earth, Sun, and as Earth goes around and revolves the Sun, it defines what we call the ecliptic plane. The ecliptic plane. So the axis of rotation has a degree, has an angle with respect to this ecliptic plane. And let me run the animation, and then you see what I'm talking about. So it's getting close to equinox. Look at this quadrant over here. Equinox, the sun is shining equally in both hemispheres. And now Earth is approaching summer solstice. The sun is shining almost overhead for somebody that is at 23.5 degrees right here. That's 23.5 degrees. Let me move this person up here and put this person right here. Right? So for somebody that is in the Tropic of Cancer, or live in a latitude that is close to Tropic of Cancer, and in the winter solstice for that person, the amount of daylight is less, because see the inclination down here of the sun's rays is very inclined. It's not shining flat on the person, and more energy of that ray is spread over a larger area. But look at what's happening here. Now the sun is approaching its highest declination, as we say, and I will talk about declination later. And when this happens, almost right there, when it happens, for somebody living in Tropic of Cancer, 23.5 degrees above equator, the sun is shining flat on that person. See that? So at noon, you could look straight up if you could, having proper protection. You could see the sun on your zenith, right on your zenith. Okay, and that's, you can see in the space what that means. And but then as Earth keeps revolving the sun, then now those light rays will fall with an angle, and more of that energy is going to be spread. I mean, the amount of daylight will diminish, and pretty much that's it. So as we go over and try to reproduce some of the basic issues, you should remember this animation. You know where to go, and so let's start first with, see if I can write here. Annotate. Just a second. Okay, let's take meridian. Let's think about, let me see if I can get a, oh, that's a good one. Okay, let's take a celestial sphere and let's go to define what could be said as the horizon coordinate system. And horizon coordinate system is based on having things in the horizon. So how can you identify in a horizon coordinate system your altitude and your azimuth angles? So you draw a circle, right? You draw a circle, and in that circle you place yourself in the very middle of it, and then you write down your horizon. That's your horizon. So this line over here is your horizon. Okay. Now let's say that you have a star right here, and you want to identify in this little sketch what is the altitude and azimuth of that star. And altitude, oops, altitude and azimuth are the two coordinate system you need to know. So the first thing you need to know is, okay, imagine this person looks straight up. If that person looks straight up, it defines a point called zenith point. Okay, so from the zenith point, that person draw a line in the sky from the zenith through the star and a perpendicular 90 degrees angle to the horizon. So this is what you see. You see that one only, right? And this angle here is the altitude. So this is the altitude right there. And you could see the angle better like here. Okay? This angle right there. And what is the azimuth? Well, if this point here, just to make it simple, if this is the north, therefore this is the south, and that should be your east, right? And that should be your western sky. So azimuth would be this angle from north to that point where the star projects itself on your horizon. This is the azimuth. azimuth. Okay. I don't know what happened. It went back. Can I go back? Yeah. Azimuth. So what's the problem with this coordinate system? It depends on location. Depends on location. So if you are in San Jose observing a star, talking to somebody on the phone that lives in Colorado, for instance, and then you say, oh, I'm observing a star that is 37.1 degrees altitude. So it's not the same for the person in Colorado, right? It's a local dependent type of coordinate system because it depends on your local horizon. So let's go to another coordinate system that does not depend on your location, and that is the equatorial uh, coordinate system. So the equatorial coordinate system is based on the celestial sphere. So now you should be able to sketch what I'm going to sketch um, right now. So the celestial sphere, how do you create a celestial sphere? So imagine you have Earth. I'm going to put a small Earth here, very small. And Earth has its axis, right? That goes like this. And I have a North Pole right there and South Pole right here. And you extend that onto the infinitive, which allows you to create a celestial sphere. Oh, that's going to be hard now. See if I can do that. So I'm kind of outlining a celestial sphere. So here's my north celestial pole. And again, you should be able to reproduce this for the quiz. South celestial pole. Okay. Now you take the equator, Earth equator like this, and then you extend that onto infinitive, very far away. So if you do that, you can define what is called celestial equator. Just take Earth equator and extend that to infinitive. That's the celestial equator. And the picture right here, I mean, has a better representation of all of that, right? Now, what is the sun? Well, the sun is an interesting fellow because for somebody in the northern hemisphere, the sun will reach the lowest possible declination here, and then 6 months later, the sun is going to reach the highest possible declination up here. So now I'm mentioning a term called declination. Declination. The symbol of declination is the letter delta, and that is an angle. So this angle is with respect to the celestial equator. So it's the angle with respect to the celestial equator. So when the sun reached this maximum declination north, as we saw in that animation, that is 23.5 degrees above the celestial equator going towards the north celestial pole. Okay? And the sun's path in the sky is something like this. And then it goes down like that. And of course, you have everything better here, right? You can see that in green. So here is the maximum declination. Okay. See this point over here? This point where the sun's path crosses the celestial equator. This is the 0 point for the system. Like in our system of latitude, longitude, the 0 point in longitude is Greenwich. in Britain. And the different local zones that we saw and I mentioned last class are counted with respect to that point. So the 0 point in Greenwich, the correspondent in the celestial equator is this point where the sun crosses the celestial equator, and this point is associated with the vernal equinox. This is spring. This is spring. Astronomically speaking, when do we define March 21st? Well, we define March 21st as the vernal equinox because that, astronomically speaking, is when, let's see if I can bring it back, is when in this space let's put us somewhere here, right? See that? Put right there. So when the sun reaches a point, let me pull this up, bring this down right here. When the sun reaches a point like here, oops, I'm not, right there. Oh, no, oh, right here. See that? When the sun, with respect to Earth, is not with respect to a latitude, but with respect to Earth, the sun shines Earth flat on the plane containing its axis of rotation, so that half above the equator and below the equator, the sun receives the same illumination. It is not with respect to a local position or a latitude, but when Earth receives equal illumination above and below equator, right here, we define this equinox. And if the sun is moving, let's see if that's the case, and if the sun is moving north, right, spring to summer, like now, so here the sun is apparently moving north, as you can see right there. So we call this vernal equinox. By definition, in this coordinate system, in the equatorial coordinate system, vernal equinox is set on March 21st. This is for the northern hemisphere, right? Of course, in southern hemisphere, the spring equinox is in September 23rd, or somewhere between September 21st and September 23rd. But by definition, this coordinate system was set on March 21st. So March 21st, we call this point in the space where the sun crosses the celestial equator and is moving north. Okay. So what is the so-called right ascension? So right ascension is the angle counted for the sun as the sun goes up over here, right? It has its projection on the celestial equator. So a positive right ascension is an angle counted in this direction with respect to the 0 point, the vernal equinox. So let's say you have a star that happens to be right here. So what is the declination and what is the right ascension? To determine the declination is similar to what we did previously to set the altitude of a star in the horizontal or horizon coordinate system. So what you do, you find the north celestial pole, From the north celestial pole, you draw a line passing through the star and crossing the celestial equator with a 90 degrees angle. So the declination is this angle right here. That's the declination. The declination is positive if it goes to north, or negative if it's south. And where is the right ascension? The right ascension is right here. Is this angle right there. Is how many hours are there between the vernal equinox point and this perpendicular. Okay. Now, let's say you have a star in the sky, and that has to do, with the sky position with respect to us. And you observe the sky in the horizon coordinate system, and you have azimuth and altitude, and you want to translate that to the other coordinate system, which is right ascension and declination. Can we do that? The answer is yes. And there is some trigonometry that I will work with you and I'll show you on Tuesday. So right now I don't want you to worry about. What I want you to do is to spend some time studying these definitions and how to sketch this on a piece of paper so you can make sense and be happy with it if that is shown. So the more you do, the better this becomes kind of okay with you. Let me give another example. This is a celestial sphere, and I'm gonna write, and I will indicate the celestial equator kind of a flat over here. So we are looking at celestial sphere edge on. So if you do a cross like that, this defines the north celestial pole, south celestial pole. Okay, so this is the celestial equator, which means if you draw circles parallel to the celestial equator, you are pretty much talking about your altitude. Your latitude, I mean, not altitude, your latitude. For instance, San Jose is of a 37 degrees latitude. So it's right here. The angle is right there. Okay. So if I draw Earth in the center like I did previously, right, like this, that's Earth over there in the center. And that's a point. San Jose is somewhere here. So the zenith point from San Jose is right there. The north celestial pole is up here. That's the zenith point for somebody in San Jose right there. Where is the horizon for that person? So the horizon for that person is you draw tangent to the person's feet right there, passing through Earth. That is the horizon. Okay. So again, horizon, zenith point, the zenith point, which makes a nice 90 degrees angle with that horizon. Now, where is the celestial equator? It's right here. 37 degrees for San Jose. But this angle over here is 90 degrees minus 37 degrees, right? And since this entire angle is 180 degrees, this is 180. This is the north celestial pole. This is the horizon, which is the due north for that person. And here's the due south for that person, right? This angle over here becomes 37 degrees. Why is that? Because this is 90 degrees. This is 90 minus 37. Therefore, this is 37. So the angle between the north celestial pole and your due north point in your horizon, that angle is your latitude, 37 degrees. Can that make sense? Can you follow this? I will review. Email me if you need me to emphasize this, but um, I I would like to play with these numbers in the observatory this coming Tuesday. That's basically what we will do. We will try to make sense of some azimuths and some altitude and try to define the celestial equator and all of these little things and take a shot at measurements basically. A little bit about time now. A little bit about time. So we saw with the Starry Night software. Let's see if I can bring it in. That there are what is called the local meridian. Local meridian. The local meridian divides the sky in two halves basically. So you look straight. There you go. That's the Starry Night. So if I can bring perhaps that's a celestial meridian. I don't want that. I want a local meridian. That's the ecliptic. That's the line where the sun is always. Altitude, that's what I want. There you go. That's my local meridian. That's my local meridian, and that divides the sky in two halves, right? So the local meridian dividing the sky in two halves pass through the zenith point right here, and the north celestial pole, which is pretty much close to where Polaris is. So let me get rid of the daylight. And Polaris is right there. So here's Polaris, right? Polaris is close to the north celestial pole, but it's not there. So the north celestial pole is right here, 37 degrees. So this angle between the north celestial pole, as I show in the previous sketch that I did, and your horizon, right there, is 37 degrees. And bring right here. Where is it? Oh, that's the one. Right there. No. There you go. North celestial pole and the horizon, where due north is, 37 degrees. That's your altitude. Now in the sky, it corresponds to this. So you find your due north, North celestial pole, 37 degrees. So from there to your zenith point is the same here. From there, the North celestial pole, to the zenith point. And if you keep going down 37 degrees from the zenith point, so if what is my zenith point? There you go, 90 degrees. So from my zenith point, now I'm looking kind of tilted. If I go 37 degrees down, 1, 2, 30, and 7 degrees down, somewhere here, that is where the celestial equator should be crossing. See if I can get that one. Celestial guide, celestial equator. There you go. So that's the celestial equator, and that is pretty much equivalent to, see the zenith? That 10, where the mark 80 degrees is, 20, where the mark 70 degrees is, 30, where the mark 60 degrees is, and 37, where the red line is. That's the celestial equator. So let's go to the sketch. I don't know what it is. Right there. So that is where the celestial equator is, right here. Right there. See? Right here. Now, if you go another 30, so North celestial pole to the zenith, and then zenith to celestial equator, 37 degrees. Now you can go down 90 minus 37 degrees to find your due south, which is 53 degrees, right? So 53 degrees, and then you find the due south. So which means you go 53 degrees down, and then you have your due south. You see that? So I will review this after our quiz on Tuesday. And then we go to the observatory and we try to do some measurements in there. Okay. So the last thing I would like to mention to you is time. I mean, I know there are so many complicated issues regarding time. It's a very complicated issue. Even in our astronomy class that we spent a whole semester, we just touched the situation, right? It's complicated, but I would like it to be able to understand some basic issue that goes on for us astronomers, and that is, one, how the 24 hours is defined. So if we go to the Starry Night software now and define our local region and go to PM, 12 p.m., 12 p.m., and I don't have daylight, right? I can show the daylight, but I'm gonna hide the daylight. I'm hiding the horizon. That's cool. So I'm hiding the horizon, and I'm also hide the daylight. Okay. So if I change now the time scale to a day, and you see the time is changing, right? The time is 12 p.m. and I'm going forward one day, every day, 12 p.m. And you see something interesting, and that is the sun one day later It's not in the same position. You see the stars every day are more to the west, but the sun spends half of the year. Let me go fast now. The sun spends half of the year in more to the right of this line and a little and more to the left of this line. Is not exactly the same, but the sun describes this so-called analemma, this nice beautiful curve. And and why is that? Well, there are two reasons for that. One is that first of all, Earth rotates with respect to the stars, not in 24 hours, but um, in respect to the stars, Earth goes a little bit less than that. Okay. In other words, let me go to a little sketch here. Um, if you take Earth, little dot in there, put the sun right here, and put its stars very far away. Okay, very far away. So if we imagine this Earth completing one turn, one spin over its around its axis of rotation, just to make it simple, with respect not to the sun, but with respect to stars that are very far away and they are a good standard to measure rotation. So you are not measured with respect to a system that is you are moving with respect to, but to objects that are so far away that they can be used as a standard and as a secure reference guide. So if this is done, um, the Earth rotates about 23 hours and 56 minutes, and that's the sidereal day. So that is in respect to the stars, that's how long the planet Earth rotates on its axis, about 23 hours and 56 minutes. In fact, we have seconds there to add, but I'm not going to complicate that. But let me show you one thing. What does it mean? Well, imagine that now I'm facing some stars in the background, and I close my eyes and allow Earth to rotate 23 hours and 56 minutes and some seconds, and that's the sidereal day. So if I do that, I'm going to click this line here, see what's going to happen. The stars will be in the same position, right? So close your eyes again and then open 23 hours and 56 minutes later. See what happened. And see what happened. And see what happened. And keep doing that. So in respect to the celestial sphere, the stars are not moving, right? But you see the sun and the planets and the moon going around because we have not only Earth rotation to be taken care of, but also Earth revolution around the sun. And that's why you're seeing the sun kind of drifting eastward. Okay. In fact, if I can bring the zodiac here, there you go. In respect to the zodiac, if we go in sidereal days, the zodiac's not moving. So here we are facing Taurus all the time. Now the sun crosses Taurus. Now you can see the nice ecliptic line in there. And that's the sun again, another year come by. And if we look at March, what is March? It's right here. March 21st. So that is the definition of the equinox point that I was mentioning before. So, in fact, I don't want to complicate your life, but just so you know that it's the equinox point is changing too because of precession. It takes a long time for us to perceive, but if I speed up time in hundreds of years, you might see this equinox point changing. But I'm not going to do it now. But because I want to be focusing on time. So 23 hours and 56 minutes is the time Earth takes to complete one rotation around its axis of rotation, and that is with respect to stars. Okay. Now, with respect to the Sun, is a little bit more or less than 24. So you have some differences with respect to the Sun. In other words, if I draw the Sun over here, right, and now I'm gonna place Earth in a circle going around the Sun like that. And this is not true because the orbital motion of Earth around the Sun is an elliptical, it's not a circle. But just to make it simple, and because it's almost an ellipse, so here's Earth and here's the Sun. And here's the star in the far background, okay? Now, 23 hours and 56 minutes later, Earth is going to be somewhere here. And that's when Earth, with respect to these stars in the background, so they are very far away, right? They are very far away. So in respect to the stars in the background, Earth completed one rotation. But guess what? So let's say you have Earth like this, pointing at the Sun. And then when Earth is here, this arrow is kind of like that. And then when Earth is there, the arrow is like that. And then when Earth is here, the arrow is like that. So you have to go a little bit further in its orbit so that in respect to the Sun, the arrow is back pointing at the Sun. You know what I mean? So the tropical day, or the mean solar day, if you will, is a little bit more than that. So about 4 minutes more than that. Okay. But it's not exactly 24 hours, as you saw in this animation that I showed before with the analemma, right? So I have to stop at 12 p.m. when the Sun is there. Up, oh, right there. Put 12 p.m. And instead of a sidereal day, I have to go one day. That's the analemma now. So now I'm going one day at a time, and then you see that there are few seconds, in fact, that of difference because of the orbital motion is not a circle, and you have all this difference to take care. So let's see how to make sense of that. Think about Earth complete one rotation on its axis of rotations in 24 hours, right? And that is equivalent to 360 degrees turn in the space, which means that every hour, so if you divide this by 24, every single hour, 360 divided by 24 is what? 1, about 15 degrees. So 1 hour in time, in local time, So the sky seems to be progressing 15 degrees westward as a result of Earth's rotation on its axis. So in the observatory, I hope to be able to convey you that. And how can we kind of estimate 15 degrees in the sky with a fist? So one fist at arm's length is about 10 degrees. So 1.5 fist is about 15 degrees. Okay, this should be okay for the celestial equator. A little bit above and below is different. How do we make sense of the whole revolution of Earth around the sun? This is Earth, and here's the sun. Well, the whole revolution of Earth around the sun takes 365 days and a quarter. In fact, it's a fascinating subject to study how we establish um, our calendrical system, which is a complicated but fascinating subject. We don't have time to do that. But you could perhaps make this close to 360. And then guess what? 360 days, a circle has 360 degrees. So that means in one day, Earth moves around the sun or revolves around the sun 1 degree. But we saw that 15 degrees of Earth rotation is equivalent to 1 hour, and that is 60 minutes. So 1 degree that Earth goes around in space is equivalent to 4 minutes. 4 minutes of time. 4 minutes. So that is the difference there is between the sun and the stars, right? So these 4 minutes is how much earlier the stars are supposed to rise every day with respect to the sun. So you keep the time, the local time, kind of flowing the same way, but stars are kind of coming up earlier, 4 minutes as a result of this the Earth revolving around the sun. Because Earth revolves around the sun, so let's say if Earth didn't revolve around the sun, Earth is here, we should be able to see stars in the same point every day. But since the stars, Earth revolves around the sun, so the stars appear to be off with respect to the sun in the previous day 1 degree. This is 1 degree. This is the same 1 degree. Now 1 degree is about what? 4 minutes in time, meaning that the stars, they rose earlier about 4 minutes. Needless to say, you guys should practice how to subtract and add times. So let's say you set up an appointment with somebody at 1 hour and 30, and you arrive, and you want to arrive there 5 hours before. That's too early. 20 minutes before, so at what time should you be there? These few things. And also the time zone, the different time zone. So if you take Earth, since Earth rotates in 360 degrees in a circle, and that's how Earth rotates, in the 1800 was Earth was divided in different time zones. So the way it goes, you take 360 degrees divided in 24 time zones, right? Each time zone is 1 hour, and that is equivalent of 15 degrees in longitude. So that also should be Should be, you should put some thoughts in there, like what's the difference in universal time between Greenwich and San Jose. So San Jose is what, 122 degrees longitude west. So in 15 degrees is equivalent to 1 hour. So 30 would be equivalent to 2 hours. 45 equivalent to 3. 60, 4, 75, 5, 80, 90, 6, 90, 105, 7, so 128. So we have 8 hours of difference between Greenwich, which is Britain, and San Jose. We are 122, and that's why different places have different flat time zone, so which is not astronomical. That's why our Nanema is kind of a off place. Anyway, so there are so many little things. Please feel free to email me if you want to ask any question. And also during my office hours, I will be happy to go through those issues with you. And so we will be a little bit more mathematics, or use a little bit more of mathematics in the class on Tuesday. So we have a quiz that will take probably between 15 and 30 minutes, and is based on terms. And the mathematics, you should be able to reproduce some of the sketches that I made. And again, if you need help, I can meet with you on Monday morning during my office hours. And so that's going to be the quiz, and then we will go to the observatory for more specific measurements. Okay? All right. Have a nice rest of weekend.